This video explains emulsion polymerization. Emulsion polymerization is a type of radical chain polymerization. The polymerization system consists of a monomer, water, which is the dispersing medium, a water-soluble initiator, and an emulsifier or a surfactant. The emulsion system is kept well agitated throughout the reaction. The surfactant molecules come together and form something called micelles once they are above the critical micelle concentration. In the micelles, the surfactant molecules orient themselves such that their hydrophobic paths are away from the aqueous medium and their hydrophilic paths are toward the aqueous medium. So this whole thing is an aqueous medium, and you can see that the blue polar heads of the micelles orient themselves toward the aqueous medium. When a micelle is formed, the surface tension of the solution drops, heat is released, and the free energy of the system decreases, and that gives it stability. Now, these are the monomer droplets. The monomer droplets also orient themselves such that their polar heads are facing towards the aqueous medium and their hydrophobic portions are away from the aqueous medium. The monomer droplets are large and they are in the order of about 1 to 10 micrometers, when the micelle sizes are in the order of nanometers. Some monomer molecules are also there in the aqueous medium, and some micelles swell up with some monomer particles. So, how does the chain initiation and propagation happen? First, the initiator releases radicals in the aqueous medium. These radicals get into the micelle and trigger the chain propagation. The chain propagation continues as the monomers inside the particle get consumed. As the monomer particles inside the micelle particle get consumed for the polymer chain formation, the monomer particles from the solution get inside to replenish, and the monomer particles from the monomer droplets get into the solution. So this progresses until all the monomer particles get consumed in the formation of the polymer chain. So again here we can draw one more example where the initiator forms the radicals and the radical enters the micelle particle that has monomer molecules and chain propagation starts. The chain keeps propagating until all the monomer molecules inside are used up, and then further more monomer molecules from the solution get into the micelle particle to replenish, and monomer droplets release more monomer molecules into the aqueous medium. So this keeps continuing until the monomer droplet concentration is almost over. At that point, polymerization is almost complete. As these micelle particles swell with the polymer chain, they also consume more and more surfactant molecules for stability. So the surfactant concentration also comes down toward the end. Thus, in emulsion polymerization, the polymerization occurs inside the micelles. The polymer particles that are formed are of the order of 0.05 to 5 millimeters, and the product is an emulsion of polymer and water, also called as latex. We can get high molecular weight polymers along with high rate of polymerization in emulsion polymerization. And increasing the surfactant concentration is one way to increase the molecular weight and rate of polymerization. Emulsions formed this way are used in floor coatings, adhesives, paints, and so on. In this video, we are going to study The plot of rate of polymerization versus time for an emulsion polymerization. The plot of rate of polymerization versus time shows three intervals. Interval 1. At time t is equal to 0, there are no particles. Particle nucleation has not started. Monomer droplets are large, and surfactant concentration is above critical micelle concentration. But the micelles are inactive. As time progresses, particle nucleation happens and number of particles increase. Polymerization occurs in the micelle particles, and rate of polymerization progressively increases. Monomer droplets become smaller in size as the monomer gets released into the aqueous medium and gets consumed by the micelle particles for polymerization. Surfactant concentration decreases, and as we approach the end of interval 1, surfactant concentration is almost close to the critical micelle concentration and sometimes even less. Coming to interval 2, we see that number of particles is a constant. Rate of polymerization is steady. Monomer diffuses into micelles and monomer droplets size progressively decreases. Chain propagation continues in the micelles, and surfactant concentration is now below the critical micelle concentration, so the inactive micelles disappear. When we come to interval 3, the rate of polymerization decreases. Monomer droplets disappear, and we have the product, which is the emulsion of polymer in water, also called latex. In this video, we are going to determine the formula for rate of polymerization and degree of polymerization in an emulsion polymerization. The rate of polymerization, Rp, is given by Rp equals Kp, where Kp is the rate constant for propagation, times m, where m is the monomer concentration, times P, where P is the concentration for the polymer particle. The concentration of the polymer particle can be written as N, where N is the number of particles per liter, times small n, where small n is the average number of radicals per polymer particle, over Na, where Na is the Avogadro number. Combining these two, we can say Rp equals Kp times m times Nn over Na. This is the formula for rate of polymerization. Coming to the degree of polymerization, degree of polymerization is given by the rate of propagation over the rate at which the radical enters the polymer particle. The rate of propagation can be written as Kp, where Kp is the rate constant for propagation, times m, where m is the monomer concentration. The rate at which the radical enters the polymer particle is the rate of initiation over the number of polymer particles. So this becomes equal to kpm n over Ri. This is the formula for degree of polymerization. We can see that we can increase the degree of polymerization by increasing n, or the number of polymer particles, or decreasing Ri, the rate of initiation. We can increase the rate of polymerization by increasing n, the number of particles, and by increasing small n, which is the number of radicals per polymer particle, and small n can be increased by increasing rate of initiation. So, if we want to increase both rate of polymerization and the degree of polymerization, we should increase n, which is the number of polymer particles. Increasing Ri, which is the rate of initiation, increases the rate of polymerization, but at the expense of degree of polymerization. The polymer particle concentration N can be increased by increasing the surfactant concentration. This video explains the Ewart-Smith theory for kinetics of emulsion polymerization. This theory takes into account three influencing factors that govern the rate of growth and size of the polymer particle. The three factors are rate of radical entry into the polymer particle, rate of radical exit from the polymer particle, and bimolecular termination of radicals. A quantity N is defined as average number of radicals per polymer particle. Three limiting cases for this N is identified. Case 1 is when N is very less than half. In this case, radical desorption from polymer particle into the aqueous phase will be significant, and this will lead to bimolecular termination of radicals in the aqueous phase. Due to this, chain propagation cannot happen to a great extent, and so the polymer particle size will be small. Case 2 is when N is approximately equal to half. In this case, when a radical enters the polymer particle, chain propagation will be facilitated. When the second radical enters the same polymer particle, bimolecular termination will happen within the polymer particle and the particle will become dormant. So this means that at any instant, only 50% of the particles will be active with chain propagation and 50% of the particles will be dormant. Radical desorption from the polymer particles is negligible in this case. Case 3 is when n is very greater than 0.5. The polymer particle will be very large in size so that more than one propagating chain is within the polymer particle, and desorption from the particle and bimolecular termination within the particle will be negligible.